Hello and welcome to my channel. Today I want to solve this problem, and it is example of an axially loaded column. So the question reads, check the adequacy of a 203 by 203 by 86 kilogram per meter universal column when subjected to an ultimate axial load of 130 kilonewton. The column is 5 meters long and is pinned at both ends. So this is the column. As you can see, it's pinned at both ends and it is 5 meters long and it is subjected to an axial load of 130 kilonewton. So let's see how you can tackle such a question. So let's write the most important information on this column so that you can rub here and create space for our calculation. So it is a 203 by 203 by 86 kilogram per meter. (86 kilogram per meter), and the axial load is 130. So axial load is equal to 130 kilonewton, and the length of the column is equal to 5 meters, like that. So let me rub here so that you can continue with this question. So solution. So we have the solution. So the first thing to do is to obtain properties. Properties of this section from the universal column table, and we will begin by the flange. We'll begin by the flange thickness. Flange thickness, which is capital T. So these properties will help you to check the adequacy of this section, if it will sustain this axial load or not. And then we have the radius of gyration. So under radius of gyration, we have Rxx and Ryy. Again, we have the area of cross section, which is AG, like that. So let us now go to the table and obtain these values. So I will show you how to obtain or how to read the table. So I'm sorry, this one is supposed to be 1300 kilonewton, like that. So let me show you how to read the table. So this is the table. As you can see, we have the serial size. This is the serial size. So we have 203 by 203 by 86. So we will come where 203 is. Here it is. Just follow my cursor. Here it is. And then 86 kilogram per meter. As you can see, that is 86. So we will come to where capital T is. As you can see, capital T is 20.5. So you will write 20.5. And then the next one is radius of gyration. We have Rxx. So we will come and check where the radius of gyration is or is located. So let's check. So that is the radius of gyration. As you can see, we have at XX, see where my cursor is. So follow that column up to the top. You will see a column of radius of gyration, and then axis XX, and then YY. So for XX is 9.27, and for YY is 5.32. And then the AG, which is the cross-section area. Let's go for cross-section area. As you can see, you have the area of section. That is the last column, and it is in centimeter square. That is 11.0. So I go to the board and write these values. So let me write this value. So capital T, we have 20.5 millimeter radius of gyration. So for RXX is 9.28 centimeter, and then for RYY is 5.34 centimeter, and then for the areas of cross section is 11.0 centimeter square. So remember, when obtaining these values, note the SI unit because they are not the same. We have others with millimeter and others with centimeter. So be keen on that. So I can come here. I want to write this information on this column so that I can rub here. So T is equal to 20.5 millimeter. RXX is equal to 9.28. This is centimeter. We have RYY is equal to 5.34 centimeter. We have the AG is equal to 11.0 centimeter square. So let's now calculate the slenderness ratio. So the slenderness ratio, slenderness ratio is given by LE over R. It can be RXX or RYY. So LE is the effective length, and for our case, our column is pinned at both ends. So it means LE is 1.0 times L. So this one is equal, which imply LE is equal to 1.0 times length. So the length is 5 meters. So you will convert 5 meters into millimeter. So LE is equal to 5, not to 5,000 millimeter. So the slenderness ratio for XX axis is equal to LE over RXX. So this one is equal to 5,000 millimeter all over 9.28. Remember, this is centimeter. So you will multiply by 10 to change it from centimeter to millimeter. So this one is equal to 53.88. 53.88. And remember, for a column which is carrying a dead load, which is GK, and the imposed load is limited to 180. So this one is less than 180. Therefore, K. Now we proceed to the slenderness ratio for YY axis is equal to LE over RYY. So this one is equal to LE is 5,000 all over RYY is 5.34 times 10. So this one is equal to 93.63, which is less than 180. Therefore, the slenderness ratio for YY and XX is less than 180. So it is okay to design such a column for a dead load and imposed load. So we now proceed to the strength of the section. So strength of the section, which is Py. So the strength of the section is determined using the flange thickness, which is T. So T is equal to 20.5 millimeter. So there is a table which guides you on how to determine the strength of the section, and it says that if T, I hope you have this table, you have the table, or let me show you the table before I continue. So this is the table, and this is an extraction from the BS 5950. As you can see, if the T, you can see where my hand is pointing, this is the T, the flange thickness, and this is the Py. This is the strength of the steel. So if the T is less than 16 millimeter, then the strength will be 275 millimeter per Newton per millimeter square. And if the T is above 16 but less than 40 millimeter, then the strength will be 265 Newton per millimeter square. And if the T is above 40 but less than 63, then the Py will be 255 Newton per millimeter square. And if the T is above 63 but below 100, then the Py will be 245 Newton per millimeter square. So you have this table. You should know, it should be on your fingertips. So let's now continue. So as you can see, this T is above 16 millimeter. So 16 millimeter is less than 20.5 millimeter. But this 20.5 is less than 40 millimeter. Therefore, Py is equal to 265 Newton per millimeter square. So therefore, Py is equal to 265 Newton per millimeter square. So we have classified the strength of this section. We proceed. So as you can see, the limit of our flange thickness is 40 millimeter. Therefore, for buckling, about x axis, we'll use 27 table 27b, and about y axis, we'll use table 27c. So again, I think you have this information. Let me show you. As you can see, you have the section type, and you have the thickness of flange and the buckling axis. So you have the rolled H section up to 40 millimeter, buckling axis. About XX you use 27B, and then YY axis you will use 27C. So we want to use 27B for XX and 27C for YY. So check for more detail, check the introduction I have just done for you. So because I want to use this slenderness ratio for YY axis and XX axis, I will write it here is equal to 53.88, and then for YY is equal to 93.63. So we know that PC is equal to AG times PC, whereby this is the compression resistance and this is the cross-section area, and PC is the compressive strength. So not these two. So this is capital P, capital PC, capital P subscript C, and this is small p. So this is the compressive strength. So this is the compression resistance. And this one is the cross-section area. So we have this one, cross-section area, as 11.0 centimeter square, but we don't have the compressive strength. So this compressive strength is what we are going to obtain in table 27b and table 27c. So this is for XX axis and this is for YY axis. For you to enter into this table, you need the slenderness ratio for XX axis, which is equal to 53.88. 53.88, like that. You also need the PY and the PY, which is equal to 265. So having these two values, we can now proceed to the table and obtain PC. So let's proceed to the table. I will show you the table. So this is table 27B or 24B of BS 5950. So you can see our slenderness ratio you can see the column. So it has different columns. Just follow my cursor. So this is column for slenderness ratio, the whole of this, and this, the remaining, this one is for the strength class. You have S275, S235, and 460. So for our case, we have our slenderness ratio of 55.88 and the PY of 265. So we will come here. This is the slenderness ratio, and if we will proceed to where 53.88 is. Of course, we don't have 53.88 here. So what we will do, we will carry out the interpolation. So 53.88 is not on what we have here on the slenderness ratio column. So we will take a value which is slightly lower than that. So this is 52, and which is higher than that, which is 54. So for 52, we'll go to where 265 is and pick this value. So this is 226. And also for 54, we'll pick this value, which is 223. And then we will interpolate. I will show you how to interpolate. So we have the slenderness ratio, and we have the 265, the value of 265. So we have from the table we have 52 corresponding to 226 as you have seen, and then our value here is 53.88 corresponding to X. We don't have a value for this slenderness ratio which is 53.88, and then from the table again we have 54 corresponding to 223. So we want to interpolate so that we can get a value for X. So you will get the difference between these two. I know you know how to interpolate, or you can interpolate in your own way, so long as you are doing the correct thing. So get the difference between 53.88 and 52. 53.88 minus 52. So this is 1.88. 1.88. And also get the difference between this and this. So this is 88. Like that. So 54 minus 52, this is 2. Also get the difference between this and this. So 226 minus 223, this is 3. And get the difference between this. We assume the difference is X, like that. So after having done so, we can do the comparison and get the value of X. So you will take 2 over 3 is equal to 1.88 over X. Then you cross multiply, which imply X is equal to, so if we cross multiply, it will be 3 times 1.88, then you divide by 2. So this is 2.82. So PC is equal to 226 minus 2.82. So this one is equal to 226. This is equal to 223.18 Newton per millimeter square. So that is our PC for X axis. This is our PC we have obtained after using the slenderness ratio for x axis. We now proceed to for buckling about the y axis. We will use table 27C. Table 27C. So buckling, for buckling, about the y axis, use table 27C. Again, let's go to the table. I will show you the table. Again, for us to enter into this table 27C, we need the slenderness ratio along the x axis, which is 93.63, and py, which is equal to 265 Newton per millimeter square. So let me show you how you obtain these values. It is the same way you have done it for the x axis. So this is the table. It is a similar table in arrangement to the table we have used for xx for the table 27b. So this is 24C or 27C. So we have our slenderness ratio as 93.63. So we will check where 93.63 is. Unfortunately, there is no 93.63. So we will take 92 and 94. Then we interpolate. 92 is slightly lower than 93, and 94 is slightly higher than 93. Then we interpolate. Then we will come here and obtain a value for 265, which is 133. See where my cursor is, and then 130. Then we interpolate. Now we'll come for so for 265, let's go for 265 in the second column. So for 92 is 136, and then for 94 is 133, like that. So 136 and 133. So we have the slenderness ratio, and here is 265, which is py. So we have 92 corresponding to 136, and then 93, which is our value 0.63. This is x, and then 94 to 133. Again, we'll do the difference between these two. So 93.63, 93.63 minus 92. So this is 1.63. Again, you get the difference between these two. So this is 2. Again here, 136 and 133, this is 3. And here we assume is x. So this is x. So we will do the comparison. 2, let me do it with another pen. So we have 2 over, this is 2 over 3 is equal to 1.63 all over x. You cross multiply, which imply x is equal to 1.63 times 3. Then you divide 2, divided by 2. So this is 2.445. Then PC is equal to 136 minus 2.445, which is equal to 133.555 Newton per millimeter square. Like that. After doing so, because we have 2PC, you have this 2PC and this one, you will choose the one which is less than the other, or you will choose the lesser value, and that is what you will use to calculate the compression resistance. So if you can compare this one and this one, we will say that this has a lesser value, so we'll abandon this one. So we will say use the lesser of the two values, and this value is 133. So PC is equal to 133.555 Newton per millimeter square. Now we can calculate our compression resistance. So PC, this is now capital P subscript C, is equal to, like that. So PC, which is the compression resistance, is given by AG times PC, and this AG is the cross section area, which is 110 centimeter square, and the PC is 133.555 Newton per millimeter square. So this 110, you'll take a G which is 110, because it is in centimeter square, you'll convert it to a millimeter square by taking 10 to raise power 2. So you multiply 110 times 10 raise power 2. By doing so, you have changed it from centimeter square to millimeter square. Then you multiply by 133.55 times 10 raised to power negative 3, because we want our answer to be in kilo Newton. So if you multiply by 10 raised to power negative 3, you are changing the whole of this into kilo Newton, from Newton to kilo Newton. You will get 1470 kilo Newton. And this 1470 is greater than our axial load, which is 1300 kilo Newton. Therefore, the section we have been told to check, which is 203 by 203 by 86 kilogram per meter will support this axial load of 1300 kilonewton. And that marks the end of the question. I'm remaining with one question, and I will be done with axially loaded column. And then after that, I will start a column supporting an axial load and bending. So we meet again in my next session, and thank you for your time.